We're going to summarize now characteristics of the Sn2 reactions in them and other videos of, say, Sn1, NE1, NE2, with the goal of understanding these reactions and then being able to predict products when we are doing problems. So first, talking about Sn2 reaction. So substitution is nucleophilic is order 2. And let's give an example here of a structure. Say I have here that's a hydrogen. Remember that will be a metal. And here I have an isopropyl. So here the absolute configuration will be priority one is the bromine, then the isopropyl, then the metal. So this configuration is S. So in this mechanism, what is important to remember is that it is concerted. And here we will have, concerted means at the same time we'll have the nucleophilic attack and the loss of a leading group. And this is what we're doing here. The attack is always on the back side. And that is important to remember because if you have a chiral center, this is your alpha carbon, this is where the attack is going to happen, backside. And then you have your products now are going to be, here you have the OH, I need to put the H on the other side, OH here bonded to the alpha carbon, and here you will have, this is your isopropyl, hydrogen, and metal here. So now notice that the configuration has changed. Here you have OH, and then second priority is isopropyl, third is the metal, so this is R. So as a consequence of the backside attack, the Sn2 reaction happens with inversion of configuration, of absolute configuration, if the attack happens at a chiral center, the alpha carbon. Now, the other thing important to notice here is that we have two molecules colliding safe in this reaction, and this is happening, these two things happen at the same time. So this reaction is bimolecular and is also rate is order 2. So we will say that rates depend on the concentration of the substrate and that of the nucleophile. That also means that the nature of a nucleophile is important when we are studying Sn2 reactions. So the stronger the nucleophile, the faster the reaction, the better it is. Another thing that is important in that we studied before is that we need, say, for this reaction, again, we need better with strong nucleophiles and better with polar A product solvent. So this we need to recognize when we're doing problems. So we need to see what the reagent is and what's going to happen with the substrate. Then, because of the mechanism, we need to remember that if the center is chiral, you're going to have inversion of configuration. Because these two events, nucleophilic attack and loss of leading group, happen at the same time. We said it was concerted. The reaction happens with one transition state. This reaction products, this is reaction coordinate. So only one step. So these are things that we need to remember. It happens with inversion of configuration, backside attack, strong nucleophile, and polar A product solvent. So we're going to be doing the same, say, analysis with other reactions. So what do we have here for a strong nucleophile? What are those? Strong nucleophiles can be OH, hydroxide. You can also have hydroxide, but also you have hydrogen sulfide, and that's also very good nucleophile. There are several. Problem with the first three here is that they're also strong bases, so they're going to give you E2 products, which we're going to see later. But these are strong nucleophiles. An example of polar A product, remember that we saw acetone is one. This is dimethyl formamide, and we will have the MSO, for example. polar A product. So we need to recognize those in the reagent and then know that what type of reaction is happening to be able to predict products when we are solving problems.